is the concept of a thermal reservoir. It is a concept, it is hypothetical, and we say that a reservoir is a system, a space or a body or a material, and ultimately it's a material somewhere, which can have as much heat transfer to or from into it, and that will of course go to another system. And in this process, its temperature will remain constant. Whatever its temperature was, you can take out as much heat as you want, you can pump in as much heat as you want, its temperature does not change. In nature, we have a few things like this, and the two biggest ones, one is our atmosphere, and the other are the oceans. Some people would think that even the earth itself, the soil, can be considered to be a reservoir. And the idea that these two are at the lowest possible natural temperature that we get, wherever it may be, these are reservoirs that are used to dump heat, dump energy from cycles. Okay, so the aircraft engine that is operating, that saw pictures of, is throwing its exhaust gases into the atmosphere. And when we do the analysis, we take that into account, that it's gone out into the atmosphere. We didn't cool that gas to bring it in, but what we did was that the compressor of the engine took ambient air, compressed it, sent it to a combustor, which expanded in a turbine, and finally this whole thing came out, and we put this whole thing in a casing. So what it did was, this air went in at some temperature which was ambient temperature. It got compressed, so its temperature went up, pressure went up. Then we burnt fuel into it, its temperature went up further. Then we expanded it here, and here it came to some other temperature, exhaust temperature TE, which we threw it out atmosphere. To develop the analysis of this, what we assume is that we have a gas or a substance which is going through this, it gets heated up here, comes out, and then that gas got cooled and came back here. So we now have a closed system, a cycle, and we can do the analysis of that. And what we are assuming there is that the atmosphere is a dump. So there are two types of reservoirs. One in which there is heat transfer into it, that is called a sink. So a reservoir at a temperature into which you can dump energy, heat, there is heat transfer to it, and its temperature remains constant. Okay, so this is the sink, and the second type of a reservoir is, this is at a temperature from where one draws heat into another system, and its temperature remains constant. And these two, so this is the source, and that's this, earlier we looked at was a sink. And we need these concepts to fully understand any of these processes that are around us, whether it's a petrol engine or a diesel engine or a power plant or a nuclear power plant. Because in all those cases, we get energy from a high temperature source, convert part of it to work, and dump the remaining into the low temperature sink. This will become more clear when we look at the laws. But the issue is, how do I create a source? Sink is easy. We can say, look, I have oceans and the atmosphere. If I happen to be in Siberia where the temperature is very low, my sink is at a low temperature, I can do many things with it. If I happen to be in India in summer, the temperatures are 40 degrees Celsius, well, nothing you can do. Nature is like that, and that's the temperature at which you have a sink. And we always work with that only in designing all these systems. Okay, so how do I make a source? Especially a high temperature source. And nature gives us only one source, and that is the sun. So the sun, we say, is a source at a temperature of about 6000 Kelvin, and this is sending us energy. So you can think of this as sun, energy coming here, and then we can do various things with it on Earth. Only a fraction of its total energy that the sun gives out ends up at the Earth's surface. Beyond this, we can say, well, okay, if I go deep into the Earth or where there is a volcano, I have hot Earth, and that is a source, so I can put water into it, get steam, and run a power plant and generate electricity. So you can say that, okay, I have a geothermal source of the Earth itself or the soil, and that I can use as a source. And this is the basis of geothermal power plants. Okay, so beyond that, there is very little by way of a natural source that we have. And so we create our own source and we say, what is an artificial source? And in all the applications that we have seen so far, in the case of a nuclear reactor yesterday, we say that the reactor can be modeled as a sort of a source. It is continuously generating heat internally, it maintains its temperature even while you take heat out of it. And that's why we say that the reactor is the source. In a coal-fired power plant, we say that the boiler or its furnace is a big entity into which we keep firing fuel, coal, oil or gas, or maybe even waste gas or garbage. It burns, generates heat, we maintain its temperature, and we keep taking some energy out of it to heat water and then make steam out of it. So that is an artificial thing that we created, and we'll model that as that the water is getting energy, or there is heat transferred to the water from a source which is the furnace where you burn the fuel continuously, and you are burning in such a way that it will give this and at the same time maintain its temperature at value that you want it. So that becomes an example of another example of an artificial source. And then the aircraft engine that I just showed, the combustor can be taken as the source, where you are again doing the same thing, continuously pumping in fuel, generating a high temperature and heating up the gas, so that way energy is taken away from the gas. Well, the difference in that is that while in these two cases, the water did not mix or have any action to do with the high temperature part of the fluid, here the gas and air actually mix and burn, and so it is strictly a process where the air got heated by something burning in it. Ideally, one can model it as the gas going in this or air going in this, and this being heated by the source. So that's another example of a source. And this example that I showed you day before yesterday, in the concentrating solar thermal plants, we use the sun, but as far as analysis of the cycle was concerned, that pipe where the water was going in and coming out as steam, this was getting heated by the sun. So you can say that this particular thing was the source. And if we store that energy, then that device would be a source for as long as the point where you are drawing energy out of it. Okay, so those are examples of a source, and the two sinks that we have with us, and we would like to go to the lowest temperature sink, we will see why, is the atmosphere and the oceans. So whenever we make work, we are always dumping heat into these. You drive a car, only a very small fraction of the energy coming out from the fuel is converted into work. The rest is dumped into the atmosphere, and when you brake the car, all the remaining work that accelerated the vehicle, that is also dumped into the atmosphere as heat. So ultimately, all of that ends up in the sink, which is the atmosphere. Okay, so that was that. Okay, the next thing I want to take up now is two things. Yeah, what is the question? Is heat always transferred from source to sink? Okay, the question is, do we always transfer heat from source to sink? Well, directly, no. But what we do, and we can make a sketch of that, is that we have a source at a temperature, a high temperature, and from there we transfer heat to a system, and from there, if the system is operating in a cycle, the symbol for that is this, and then we dump some of that into a sink, and the balance comes out as work. So this is a system working in a cycle. On a continuous basis, this will happen, and that's how we continue electricity. The opposite is also possible, and that's what a refrigerator does. You have a sink, which is your refrigerator inside, or in the case of an air conditioner, it is the inside of the room, which is the low temperature body, which is the sink. We put work into this, which is what you're driving the compressor with. We extract, heat is transferred from this to this, the system, and then all of that is dumped into the surroundings, which is the source. So how does this heat transfer take place? Well, inside this, what one does is you have air, but inside this you make a tube where the temperature is lower than this temperature. And then it goes out its temperature and dump that heat to the source after it is compressed. So for this heat transfer to take place in the system, the temperature here must be less than TL, the temperature here must be greater than TH. Only then the system will work. Okay, so if you add that, we can look at one more thing, which is that if I want heat transfer to take place over a very small temperature difference in a reversible way, then the closest that one can get is to say that, look, I have a material flowing in this, and as we add heat to this, its temperature does not change. And intuitively one would say, no, this is not possible. If I heat something, its temperature got to go up. But we have one thing which we exploit very, very heavily, which is that if a substance here, what you see in everyday life, say like water is going in here, we heat it and it comes out as vapor. And during this process, the pressure is same. During the evaporation process, the temperature is same. That means anywhere at this point, wherever we were adding heat, the temperature was also the same of the substance. And now we get one control that the system's temperature is pretty much constant. To make the process externally reversible, we select that this heat transfer is taking place from surroundings whose temperature is, say, T plus delta T. And as we make delta T very, very small, we are getting the closest we can to reversible heat transfer. And so in many, many applications, we try to exploit this fact that if I can get evaporation or the opposite, which is condensation, I can have heat transfer at constant temperature. So this is heat transfer at constant temperature, and that's a thing we will exploit very heavily. And that's what I came to this point, because here that's what happens in your air conditioners and refrigerators. There is phase change taking place in both of these. So this is at a low temperature taking heat from here. This is at the high temperature transferring heat there. Okay. So the question here. Okay, so that will answer. So directly putting heat from source to sink, it doesn't give us any advantage at all. Of course, if our objective is to cool something, say you have a microprocessor that is operating, it is generating heat and we want to cool it. So you can say that the microprocessor is a source. On that you put a heat sink and you put air blowing on it, and so we are cooling it. So the microprocessor is the source, the surrounding air is the sink, and we are directly dumping heat from source to sink. And the objective there is not to make power or anything, but the objective there was to keep the temperature of the chip below a certain temperature so that its life is prolonged and it doesn't it at least survives that much longer. And by the way, that is a very, very hot research area, because the whole technology that you see around you every day, new mobile phones with all sorts of things coming into it, this was completely unimaginable years back. Now we are not just able to make chips and drive them fast and have software and hardware for it, but the most crucial thing is we are able to cool them. That's where the breakthroughs are still coming. And it's going to happen for the another 20 years. And this idea also tells you that if you are producing like the aircraft engine picture that I made, this also tells us, and that when we look at the laws, it will become much more clearer, that in this, the peak temperature we got, say this source generated the peak temperature, and say this is T combustor, say TC, and thermodynamics will tell us that if I keep increasing this, the efficiency keeps going up. Same thing with the power plant boiler. So I showed you some data day before yesterday to show you that when the first turbines were made, this temperature was of the order of 700 degrees Celsius. And I mentioned that now we are already working with 1700 degrees Celsius. And in the next 20 years, we are probably likely to see this go up maybe 2100 degrees Celsius. And because of this, all aeroplane engines and stationary gas turbines which are generating electricity, they're all becoming more and more efficient. The same amount of fuel being burned, more work being produced. So historically, what has happened here is that about every 7 years, this temperature goes up by 100 degrees Celsius. That's a lot of research that goes on. We have teams of a few hundred people working on it, many of them with doctorates. A lot of money is required to do this. The corporations have a commitment that we will do it, and they are the leaders in making these engines. Same thing happened with coal burning power plants. Starting early on with temperatures of 300 degrees Celsius, about in the 40s and 50s, we now have reached 550 degrees Celsius 25 years ago. Then after a lot of R&D, we were able to extend this to 565 degrees Celsius. And now, with climate change being a major issue, there's a lot of R&D now going on to push this to 710 degrees Celsius. This is a great research challenge. You have to look at completely new sets of materials, new machinery, new ways of manufacturing, and be able to predict how this will work. And all these things is not something that works for a few days. When we say that the technology has matured and come into the market, it means research went on for 7 years or 10 years. And once it comes into the market, as a user, you can use this non-stop for thousands of hours. We want to make a power plant with this thing, which will run non-stop for 1 year at least. And we do maintenance on it and run it for 25 years. That's where technology becomes the challenge. But the point of talking about this is that the motivation for newer engines that you see coming around you, motivation for new power plants coming around you, air conditioners, refrigerators coming around you, and practically everything else coming, in some way or the other, comes from these motivations of thermodynamics. So this is only the starting point. After that, there's a lot more from different knowledge streams that happens to make the product.